In this presentation, I will be discussing the paper on cryofuge for cold collision experiments with slow polar molecules. The winner of the 1981 Nobel Prize for Physics, Arthur Schawlow, once said, "A diatomic molecule has one atom too many." While this would make some quantum mechanics calculations far simpler, this would prevent the study of interesting phenomena in the field of cold atoms and molecules. So, what do we mean by cold? Cold atoms and molecules refer to phenomena in the range of a few Kelvin to millikelvin, while ultracold refers to temperatures below the millikelvin scale. In the past few decades, cold and ultracold atoms have produced novel results such as Bose-Einstein condensates, and more recently strongly correlated systems such as cold atom Fermi-Hubbard antiferromagnets. The success of this has inspired research into cold molecules. The cooling of molecules is not simply done for its own sake. One of the aims of cooling molecules is to access and study unique quantum phenomena, where molecules have large de Broglie wavelengths comparable to their sizes and separations. This mirrors the early work by nuclear physicists in the 1930s, where scattering, resonances, and tunneling became key features used to examine nuclear collisions. For cold molecules, this level of equivalent wavelengths is far more difficult to reach. So, why do we want cold molecules? Well, cold molecules are the focus of many researchers as they allow more complex and intriguing phenomena to be accessed than would be available using atoms. At the simplest level, this includes fixed electric dipoles. However, the complexity of the large number of internal degrees of freedom possible in polar molecules means they have been suggested as candidates for qubits in quantum computers. High-resolution spectroscopy on states of cold molecules can also be used to measure variations in the electron-to-proton mass ratio. Current research by Ospelkaus et al. Has examined the effects of quantum statistics on chemical reactions of potassium-rubidium molecules. Other experiments by Tisniti et al. Have studied the reaction between fluorine radicals and hydrogen molecules. The measurement of this reaction at 11 Kelvin complements quantum scattering calculations of the same molecules, which give very agreeable results. Cold collisions of molecules also help to answer some questions of efficiency and energy transfers of molecular collisions, and the feasibility of chemical reactions at lower temperatures. The most evident difference of cold collisions with warm is their much longer de Broglie wavelength, as previously mentioned. However, the difference in elastic scattering is also stark. In the warm regime, elastic collisions possess large orbital angular momenta. However, in the cold regime, collisions only involve an S-wave phase difference, which in a sense can simplify the calculation of scattering length. Cold molecules can be prepared directly by cooling down hot molecules to the cold or ultracold domain, or indirectly by first preparing cold atoms and then reacting them to produce cold molecules. An example of direct cooling includes buffer gas cooling, which we will discuss shortly. However, there is a problem. We would like to prepare samples that are cold, dense, and slow in order to distinguish quantum phenomena from thermal physics. However, this has only been possible to achieve using alkali dimers, not naturally occurring molecules. Attempts have previously used naturally occurring molecules, which produce a dilemma between cold, dense, and fast molecules, or cold, dilute, and slow ones. However, the authors of this paper devised a novel solution to produce cold, slow, and dense polar molecules. How did they achieve this? Using a cryofuge, of course. Cryofuge is essentially a combination of two technologies: successive buffer gas cooling and centrifuge deceleration. In Wu et al.'s paper, we will examine the mechanism of the cryofuge and explain its ability to produce cold, slow, and dense samples capable of selecting for state purity or molecular flux. The first component of the cryofuge is The first component of the cryofuge is buffer gas cooling. First performed in 1984, buffer gas cooling has become a widely applied technique in the field of cold atoms and molecules. It is capable of producing slower molecules and in some cases higher molecular flux than is possible with supersonic expansion or other techniques. This is done by mixing the target molecules in a cell with a buffer gas at around 2 to 20 Kelvin. The buffer gas must have a specific number density in order to prevent three-body collisions at higher densities and must also be low enough to thermalize the target molecules. This reduces the number of populated states of the molecules, as you can see in the figure here. J represents the rotational quantum number, with K being its projection on the molecular symmetry axis. The cooled molecules can then be selectively extracted using a quadrupolar guide. However, the use of the buffer gas cooling presents a number of issues. Firstly, the slowest molecules cannot be extracted due to collisions from the buffer gas, and it is also not possible to produce molecules which are slower than around 150 meters per second without vastly increasing the velocity distribution and decreasing the molecular flux. This brings us to the second technique incorporated into the cryofuge, centrifuge deceleration. Centrifuge deceleration for continuous beams of molecules is a relatively recent technique, which is capable of slowing molecules to around 15 meters per second. It does this by injecting polar molecules into an outer ring, which allows the centrifuge to operate continuously. Guides are then used to direct the molecules. These are electric quadrupoles, which will only work for polar molecules which have permanent electric dipoles. A cross-section of these guides can be seen on the bottom right, where the color scale shows the electric field strength. The polar molecules are guided at the center of the field, where the electric field strength is lowest. The central spiral arm rotates around the outer ring, another quadrupolar guide, which redirects the molecules into the spiral. This is done using the spiral guide axis seen on the top right. The electric field here is continuous, which allows a seamless transfer into the rotating spiral arm. The deceleration occurs as the molecules travel towards the center of the spiral. Their kinetic energy is converted to potential energy, given by the equation in the bottom left, where omega is the angular velocity of the rotating spiral arm. From the rotating frame perspective, this deceleration is not caused by the electric quadrupole, only by the centrifugal potential, as the electric field is always perpendicular to the quadrupole guide path, and therefore the molecular velocity, and so applies no force. However, if we consider the laboratory frame, then the electric force does cause the acceleration, as the electric force vector is not perpendicular to the molecular velocity, and so a component opposes it, slowing them down. Finally, the decelerated molecules are removed from the centrifuge by a quadrupolar guide. This exit curves upwards at the center of the rotation axis. The exit bend here also acts as a high velocity cutoff, as fast molecules are unable to remain in the quadrupolar guide round the sharp exit bend. Centrifuge deceleration is capable of producing high fluxes of slow-moving molecules. However, the system has no way of cooling them down. Returning to the cryofuge, it operates as warm molecules at around 200 Kelvin, first thermalized with a buffer gas, typically helium at 6.5 Kelvin or neon at 17 Kelvin. This initial cell can operate in two regimes, the boosted regime and the supersonic regime. The boosted regime operates at an intermediate flow rate somewhere between the effusive and supersonic regimes. In this figure, the boosted regime is labeled as buffer gas. At the aperture of the cell, the cooled molecules interact with the buffer gas, boosting the cooled molecules as they exit the cell, hence the name boosted. As the flow rate increases, the speed of the cooled molecules exiting the cell becomes fully dependent on buffer gas atoms. This is the supersonic regime. You can see some further differences between the two regimes. Supersonic is higher pressure compared to the boosted regime. The boosted regime gives a higher flux than the supersonic regime. However, the supersonic regime also produces a higher state purity than the boosted. The molecules are then extracted out of the buffer gas cell and using a quadrupolar guide are directed into the centrifuge. This guide contains a turn which allows the target molecules to be redirected using the quadrupolar guide while the buffer gas atoms are separated from the system. The centrifuge then operates as before, slowing the molecules using the spiral arm. The slowed molecules can then be inserted using a quadrupolar guide, the time of flight guide, into a detector, which in this case was a quadrupole mass spectrometer. To validate their setup, Wu et al. Performed several experiments. These included independent buffer gas cooling, measuring the velocity distribution and molecular flux of the cryofuge for a variety of polar molecules, and examining the collisional loss of the system for various molecular densities. This data here looks at the cooling of the rotational states of fluoromethane in both the boosted and supersonic regimes from buffer gas cooling. The boosted regime is shown on the left, while the supersonic is on the right. For both of these regimes, increasing the density of the buffer gas increases the state purity of the cryofuged molecules, as seen on the horizontal axis on the right. In these regimes, the population of the 1,1 state increases. The left-hand horizontal axis contains J and K, the rotational quantum number, and its projection on the molecular symmetry axis, as before. From this, we can see that the supersonic regime has a much higher state purity across all values of buffer flux, while the boosted regime maintains its higher overall flux. The authors then applied the cryofuge to fluoromethane and recorded the velocity distribution for the various values of centrifuge rotation speeds, which you can see here. This was done using fluoromethane. From this, we can see that the most probable value of the velocity decreases as the rotation speed of the spiral increases. However, beyond a certain point, about 30 Hz, the molecular flux begins to decrease as some of the molecules are no longer moving fast enough to overcome the centrifugal potential and reach the detector. The opposite of this can also occur, as some molecules in the supersonic regime can move too fast for the spiral guide to redirect the molecules into the spiral arm. In order to demonstrate the cryofuge was actively slowing molecules in the system, the effect of deceleration was also measured. Here you can see the velocity distributions of the input and output of the cryofuge on the left, and flux values of the boosted regime and the supersonic regime against rotation speed on the right. You can see the input distribution has a much larger peak centered at 165 meters per second compared to the output, which has a smaller peak at about 25 meters per second. Note here that the input distribution has been rescaled by a factor of 0.2. This does show that the cryofuge is indeed slowing down the molecules, instead of merely selecting for slower ones. The large difference in peak height is explained by the high rotation rate of the cryofuge at 62 Hz, which for the 20 cm spiral arm used corresponds to 78 meters per second, meaning many molecules inputted would not be moving fast enough to enter the rotating spiral arm. The ratio of the height of the peaks can then be used to calculate the efficiency of the cryofuge, which was around 8% for the supersonic regime shown here and 20% for the boosted regime. This higher efficiency for the boosted regime is due to its lower input velocities, which allowed a larger fraction of molecules to be guided into the rotating arm. An important result from this paper is the high flux of the molecule's load. For fluoromethane, these values are around 10 to the 9 reciprocal seconds for a 30 Hz rotation speed at below 1 Kelvin, which are around 10 times larger than the initial demonstrations of continuous centrifuge deceleration. If the population of only a single quantum state is considered, then the flux is 1000 times higher than in typical centrifuge setups. The authors repeated this procedure for deuterated ammonia and trifluoromethyl acetylene, giving fluxes of around 10 to the 10 seconds and densities of around 10 to the 9 reciprocal cubic centimeters below 1 Kelvin. Methanol and isopropanol were also examined using the same method. The flux for methanol was measured at about 3 times 10 to the 8 reciprocal seconds with a peak velocity of 40 meters per second below 1 Kelvin. The flux of isopropanol was around 10 to the 8 reciprocal seconds, also below 1 Kelvin. However, this was more difficult to maintain due to the lower vapor pressure, meaning it was liable to freeze. Due to the high density of cooled molecules, cold collisions occurred after the deceleration in the time of flight guide between the spiral arm and the detector, as well as in the centrifuge and guides. The loss can then be modelled based on the velocity distribution. This velocity distribution after collisional loss can be written like so, where P0 is the original velocity distribution, N is the molecular density, L is the guide length, accounting for the length of the centrifuge, and K loss is the loss rate coefficient, which is a product of the collisional cross-section and the relative velocity of colliding molecular pairs. From this, the ratio of two velocity distributions can be calculated for various changes in molecular density, fitted by this equation, where alpha is a fit parameter accounting for the difference between theoretical and experimental loss, and kth is the theoretical loss, which includes both elastic and inelastic contributions. These contributions were calculated using an individual model for each of the elastic and inelastic coefficients. This can be seen on the left-hand graph, where various molecular density differences and their fits are shown along with a no collision fit for fluoromethane. The initial fluxes of fluoromethane are color-coded below the figure. The right-hand side shows the same for deuterated ammonia. Here we can see for both molecules that the no collision fit drops off at higher velocity values along with different molecular density values. This is due to the filtering of the exit band. Additionally, the fluoromethane data shows an increase of collisions and losses at higher initial molecular densities, as higher fluxes increase the probability of a collision occurring. The calculated loss rates were around 30 and 40% smaller than the measured elastic and inelastic rates respectively, due to an underestimate of molecular density in the centrifuge. From this, the authors calculate that only 1 out of 17 elastic collisions leads to molecular loss. Finally, the authors note that further use of electrostatic traps could be used in conjunction with a cryofuge to measure the thermalization rate of different states and collision energies. The use of ChemPhys cooling, which is the driving of molecules around a unidirectional cycle to remove excess energy, would also allow lower temperatures to be reached and explore the scattering resonances at the threshold limit, and perhaps even evaporative cooling of polyatomic molecules. Generally, the authors conclude that the cryofuge is very versatile and could be applied to a wide range of cold molecule research, suggesting uses in laser-cooled diatomic molecules, which the first two of these papers examine, and measuring the proton-electron mass ratio as mentioned previously, which the last paper deals with. A cryofuge is ideally suited to handle these. In the first instance, due to the rotational states of the diatomic molecules possessing large start shifts. In the second instance, the cold, slow beams produced by the cryofuge here are ideal, as previous techniques have used polar molecules such as methanol, which our paper also use. However, in order to attain some exotic quantum phenomena, a high phase space density is necessary, that is, the number of particles per cubic thermal de Broglie wavelength. Cryofuges are only capable of producing molecules with low phase space densities, and as a result, dissipative cooling techniques such as laser or evaporative cooling are necessary to produce high phase space densities. So, where to next? This looks to be a very intriguing technique. However, at the present moment, no further research has been carried out using this cryofuge. Nevertheless, in the future, it may become a workhorse of cold molecule research.